Ooga chaka, ooga, ooga, ooga chaka, ooga, ooga, ooga chaka, ooga, ooga, ooga chaka, ooga, ooga, I can't stop this feeling deep inside of me. Girl, you just don't realize what you do to me.
Good morning, good afternoon, good evening, whatever the case may be. We are back, and we are better than ever, and we are going to talk about groups today. It's going to be outstanding. You are going to be hooked on a feeling after we're done with our exploration of groups. You will be in love with groups. Anyway, I digress, or I ramble. Same thing? I don't know. Let's get to it, shall we? So, we're working on here is formally defining what it is that is a group, okay? And in order to show, or in order for a set to be a group, it has to adhere to 4 axioms, okay? So let's start up here. A set with one or more operations defined on it is called a structure. And then within the set of algebraic structures, there is a hierarchy. An algebraic structure with one closed binary operation defined is referred to as a groupoid. If it obeys associative law, it's promoted to a semigroup. And a semigroup with an identity element is a monoid. And in some of those monoids, each element will have an inverse. And this leads us to groups. And what we're interested in, what we're focusing on here, is whether we have a group or not. Okay, so the formal definition is here, and then we'll jump right to an example. A non-empty set G on which a binary operation star is defined is said to be a group written with this notation if each of the following 4 axioms hold. And we already know these. We've learned these. G is closed under the binary operation, which we already know about. It is associative, which we already know about. It has an identity element, which we know about. And each element, here's the biggie, each element of the group has an inverse under the operation, which we know about as well. Okay, and then here's a nice little thing for a group. Under the operation, under this operation, under the operation star, if it is clear which operation is the relevant group operation, the group will sometimes be referred to simply as a G. It's mathematics. We like to be efficient. All right, so behold the Cayley table, and it's for the operation star. So when we take E and we operate B, we end up with B. So just, we don't know what's going on here exactly. We could probably figure it out, but we shall, we'll just go with that simplistic view. C star A gives us X and so on. Okay, so we have to show that S is closed under star. Okay, and no, you don't have to show you don't have to write out every single element and list them out and do a checklist or anything like that. All you have to do is, by inspection, see that all of your results in here are in here, if they show that. And it is. Every answer here, I mean, you should go through and check every single letter, of course. You can't just glance at it, but you don't have to write that out, okay? Once you are confident, or you're sure, that S is indeed closed under the binary operation, you can just simply write it like this. For all A and B, which are elements of S, right? When the operation is performed, A star B is an element of S. Okay? Therefore, or as required, S is closed under the binary operation, which I always say is star. Okay? So that's all you need right there. There was something I was going to add. It'll probably come back to me. Oh yeah, that's this. Don't, this A and B is not this A and B. Remember, we're just generalizing here. Okay. Sometimes folks get confused with that. Part B, there is an identity element for star and S. Okay. So, let's see. A, B, C, D, X. Oh, we're lucky. It's right here, and it doesn't occur again. So that means that the identity element, what do I operate on? E star E gives me E. A star E gives me A. B star E gives me B. So the identity element is E. So in order to talk about this, we have to introduce a new variable, or I'm sorry, in order to show it, we would do it like this. For all y element of the set S, E star y is equal to y star E is equal to y. Okay, so as required, since E is an element of the set S, the identity is E. And I think you probably realize why we have to use a different variable than what is here. Y is representing all of these and isn't one of them. So if I said something confusing like C, when we're talking specifically about the identity element, we have to use a different letter to represent all of the all of the candidates there. All right, so the identity is E. Giddy up. All right, C. Each element of S has a unique inverse. Okay, so again, you do not have to list them. You just have to state what it means to be to have a unique inverse. So remember, we just have to find all the E's, right? And it's very nice that it's in a diagonal here. So E star E is equal to E. A star A is equal to E. B star B is equal to E. So everybody has their own unique inverse. In other words, I operate and I get the identity, and that's what it takes for there to be each element having a unique inverse. So you state it like this. Again, for all y, an element of the set S, y star y is equal to E because they're all self-inverses, so that's why it's y star y. So as required, each element has a unique inverse itself. So it's a self-inverse. Okay, and finally, star is not associative. Show that star is not associative. Thank goodness we don't have to show it is associative. We only have to show it is not associative. Okay, so we just have to, let's see, we have to come up with a counterexample to show that it's not associative. So let's do A star, B star C. And sometimes you just have to pick and choose. Okay. So this is equal to A star. Well, what is B star C? B star C is equal to X. So I work within the parentheses first, and this turns into A star X. Okay. And what does A star X equal? A star X is equal to B. So that equals B. Okay. So now I'm going to show a counterexample. So I'm showing a counterexample, so I'm going to move the parentheses here, star C, and show that it does not equal B. So A star B, what is A star B? A star B is C, so this becomes C star C, right? And we already know what it is because these are self-inverses, but let's just make sure C star C is E. It's the identity element. Okay, so we have shown it, and to formally state it, we could do something like this. A star B star C equals C star C equals E, which is not equal to A star B star C. Okay, and then you could say something like, hence, star is not associative. And then the other thing we know about this that they don't ask is that since it is not associative and it does not meet the requirements of all four of those axioms, it is not a group. If it was associative, then it would be a group. Okay, so one more thing. Abelian groups, sorry, and Abelian group, I keep mispronouncing it. An Abelian group is a group which has the commutative property. The set of Abelian groups is named after Niels Heinrich Abel. Abelian. I have to find out how to pronounce it. I'm killing it. So a group is Albion if A star B equals B star A for all A, B element of G. So this is very, very simple to tell. I hope you realize if the Cayley table for group G is symmetric about the main diagonal, then A star B equals B star A for all A, B element of the group, and the group is abelian. Okay, so here we go. Show that the set Z5 symmetric difference, that is 1, 2, 3, 4, forms a group under mod 5 multiplication modulo 4. So this is the integers, right, through 5, not including 0. So that's why it's 1, 2, 3, 4. Okay, so we have to make a Cayley table, yes. So, and behold the Cayley table! So we're showing that it forms a group, and we're also showing that it's all abelian. So let's take a look at the main diagonal. Is it commutative? Let's go here, and it is symmetrical. So we have done the commutative axiom. Okay, so commutative, commute, check, right? Is it closed? We'll do the easy ones first. Are all the results here and here? Yes, it is closed. Okay. And I'm not writing out the things before just that I did in the previous example. You saw that. Okay. Does it have an identity? Does it have an identity? Okay. Let's see. Blah, 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 blah. So I need 1, 2, 3, 4. I have 1, 2, 3, 4. So yes, the identity is 1. It equals 1. And does everything have a unique inverse? Right? Does it have an inverse? So now we're getting to the dicey proposition. So I'm going to circle all the ones where the operation yields an identity. So 1 mod 5 1 results in a 1. 2 with the operation of 3 gives me a 1. 3, 2 is a 1, so we went 2, 3, and 3, 2. And then 4, 4 is a self-inverse. So yes, every element has its own unique inverse. And what about associative? Well, we could possibly, but we do not want to spend all the time working out all the possibilities, and you can see what a mess that would be from the last group. Okay. Oh, we already answered this. This is yes. So is it associative? Well, guess what, boys and girls? All we are doing is multiplying integers, and whether you're multiplying integers in which you're used to doing in the base 10 system or mod 5, multiplication is associative across all the modulus. So associativity follows from the associativity of multiplication of integers. So guess what, boys and girls? We have a group. Giddy up. Now, we didn't need commutative. Sorry, that's not one of the axioms. That just shows me that it's an abelian group. But we have closed, we have identity, we have inverse, and we have associative. So we have shown that it is a group. And I think that deserves a little bit of a celebration. We will go out with Hooked on a Feeling. I hope you enjoyed it. I certainly did. I am hooked on the feeling of groups. Hope you enjoyed it. We will see you next time. And until then, I am